With every new discovery, the universe keeps challenging us. Despite today's technological advancements, many gaps remain in our understanding of the macrocosmos. Unexplored phenomena in the farthest reaches of our galaxy continue to both horrify and amaze deep space researchers. Hello and welcome to Z. Please don't forget to subscribe and hit the bell icon. Today, we will discuss one of these phenomena. The most powerful magnets in the universe, known as magnetars, which emit incredibly high levels of radiation. Mankind has encountered extremely powerful radiation from deep space several times in the past 50 years. However, as is often the case with space discoveries, the source was slow to be identified by astrophysicists. In 1979, 3 U.S. Vela satellites monitoring nuclear tests on Earth detected an unusual gamma-ray flare. In 1992, astrophysicists hypothesized the existence of a previously unknown celestial object with a massive electromagnetic radiation coefficient. In 1998, a gamma-ray flare in the constellation Aquila was recorded by several devices, pinpointing an anomaly tens of thousands of light-years away. In 2004, all telescopes worldwide were briefly dazzled, and less than a second later, every cubic centimeter in the solar system was hit by a wave of gamma-ray radiation, the most massive burst ever recorded. Today, we are closer than ever to understanding the nature of this phenomenon. A magnetar is a neutron star with an incredibly powerful magnetic field of about 10 to the power of 13 teslas, which is trillions of times stronger than Earth's electromagnetic radiation. It is also one of the rarest and most dangerous phenomena ever discovered by humanity. When a supermassive star nears its end, it can explode as a supernova. Among the various possible outcomes, only one scenario leads to the formation of a magnetar. Many of you may have heard of Russian roulette. In this game, only one cartridge is placed in the revolver cylinder. The chance of firing is low, but the consequences are extreme. Similarly, scientists are still debating the exact process leading to magnetar formation. One theory suggests that the star's internal energy and rotational energy influence magnetar formation. If a neutron star forms while spinning rapidly, its internal and rotational energies create a powerful magnetic field within the first few seconds, a process known as the dynamo mechanism. Another theory posits that a magnetar may receive energy from another star after the accretion process. Scientists have identified a magnetar on an escape trajectory from our galaxy, suggesting it gained energy from a companion star in a binary system. This is similar to a basketball spinning around the rim before falling. The spin determines its fall direction. Magnetars spin extremely fast, between tens and thousands of times per second, and their sizes are very small, with diameters typically between 20 and 30 kilometers. For comparison, the Moon's diameter is 3,474 kilometers, about 173 times larger than an average magnetar. However, a magnetar with a diameter of 15 kilometers would be significantly heavier than the Sun due to its incredibly dense interior, which causes its high magnetic radiation. For example, 1E 1048.1 to 5937 is an anomalous X-ray pulsar 9,000 light-years away in the constellation Carina. The star it evolved from was 30 to 40 times the mass of the Sun. The matter in these stars is so dense that a pin cap would weigh billions of tons, and a human would be torn apart in seconds upon landing on its surface. Several years ago, NASA astronomers registered a phenomenon known as a starquake. The Fermi Gamma Ray Space Telescope detected intense X-ray bursts from magnetar SGR J1550-5418. This star's magnetic field is so powerful that its crust occasionally bursts, releasing vast energy. Such starquakes generate pulsed electric currents. In theory, if an active magnetar entered the solar system, we wouldn't notice the threat as Earth's ozone layer and all life forms would be eradicated in milliseconds. Fortunately, the nearest magnetar is at a safe distance. Approaching a magnetar is challenging due to its core's gravitational properties and energy flares, Even in a stable condition, its magnetic field can disrupt electronic devices hundreds of thousands of kilometers away, and within 1,000 kilometers, any object would be reduced to atoms. Scientists classify magnetars into two types using abbreviations: SGR, soft gamma repeater, and American Express, anomalous X-ray pulsar. Essentially, SGR and American Express are different phases in the life of the same object. Initially, a magnetar exists as an SGR for the first 10,000 years, visible in regular light and emitting soft gamma rays. As it ages, it exhausts its properties and becomes visible only in the X-ray range as an American Express. Today, the number of known potential magnetars ranges from 30 to 150 among billions of neutron stars. About 12 are in the Milky Way, with the closest, SGR 1806-20, located 13,000 light-years away. This magnetar is a soft gamma repeater, and a starquake on its surface would only cause slight changes in Earth's ionosphere. Due to their small size and distance, magnetars can't be observed with amateur telescopes. Infrared or X-ray scanning is used to detect them. However, their magnetic fields and radiation make them easier to find with various instruments. In 2013, astronomers discovered a magnetar near a supermassive black hole in the Milky Way's center. Detected by orbital telescopes including the Chandra X-ray Space Observatory, SGR 1745-2900 is only 0.3 light-years from the black hole. It's the only neutron star found near such a massive object. Scientists have observed SGR 1745-2900 since its discovery. Its X-ray radiation levels are lower than expected, sparking debate about whether the black hole influences it. After 2 years of observation, astrophysicists concluded that the 0.3 light-year distance is too great for magnetic or gravitational interaction. The cause likely lies elsewhere. A magnetar's lifespan is short, about 1 million years, and its magnetic field naturally weakens over time. Some scientists believe these processes cause the star's status change. Magnetars can switch categories, flare up more or less frequently, and deplete their matter, transitioning from SGR to American Express. A former magnetar may become a different type of star, a thermally emitting neutron star, after its magnetic field dissipates. Only about 7 of these are known to science, dubbed the Magnificent Seven. Each may once have been one of the most dangerous objects in deep space. To fully understand them, we need more time, technological advancements, and dedicated researchers to solve the universe's most dangerous and incredible mysteries. A magnetar is an extraordinary type of neutron star, known for its incredibly powerful magnetic field. These fascinating celestial objects are formed from the remnants of massive stars that have exploded in supernovae. With a diameter of only about 15 kilometers, roughly the size of a small city, magnetars are incredibly dense and possess magnetic fields that are billions of times stronger than any magnet created on Earth. Formation and characteristics. Magnetars are born from the core collapse of stars that are at least 8 to 10 times the mass of the Sun. When such a star exhausts its nuclear fuel, it undergoes a catastrophic explosion called a supernova. The core left behind is so dense that protons and electrons combine to form neutrons, creating a neutron star. In the case of a magnetar, this neutron star has an exceptionally strong magnetic field, which is thought to arise from the dynamo effect during its formation. Magnetic field strength. The magnetic field of a magnetar can reach up to 1, 0, 15, 10, 15 Gauss compared to the Earth's magnetic field, which is about 0.5 Gauss. This means a magnetar's magnetic field is a quadrillion times stronger. Such an intense field can have dramatic effects even from a great distance. For instance, it can strip atoms of their electrons and distort the shapes of atomic nuclei. Dangers and effects. Magnetars are considered among the most dangerous objects in the universe due to their extreme magnetic fields. If a magnetar were to pass within 1,000 kilometers of Earth, its magnetic field would disrupt electronic devices and the structure of matter itself. Even at a distance of several 100,000 kilometers, a magnetar could erase data on magnetic storage devices and severely disrupt global communications. X-ray and gamma-ray emissions. Magnetars are also known for their erratic emissions of X-rays and gamma rays. These emissions are caused by starquakes or the reconfiguration of the magnetic field. Such bursts can release more energy in a fraction of a second than the sun emits in 100,000 years. These high-energy emissions can affect satellites and pose a threat to astronauts. Observations and examples. The first magnetar was discovered in 1979, and since then, about 30 magnetars have been identified. One of the most well-known is SGR 1806-20, which emitted a giant flare in 2004 that was detected by numerous satellites. This flare was so powerful that it briefly altered the Earth's ionosphere from 50,000 light-years away. Conclusion: magnetars are some of the most mysterious and formidable objects in the universe. Their tiny size belies their incredible power, with magnetic fields that can disrupt matter at a fundamental level and emissions that outshine entire galaxies. As we continue to study these enigmatic stars, we gain a deeper understanding of the extreme conditions and forces at play in the cosmos. Thank you for watching and see you next time.